Hello, everyone. We'll start the webinar in about 1 minute. We're just waiting for people to get in and get settled. Hello, everyone. We'll start the webinar in about 30 seconds. We're still waiting for people to come in and get settled. Hello, everyone, and welcome to today's Safety and Health Magazine webcast, Low Voltage Arc Flash and Electrical Shock Safety for High Voltage Qualified Persons, sponsored by eHazard and Bulwark. This is Alan Ferguson, Associate Editor of Safety and Health, and I'll be moderating today's event. First, thank you so much for joining us, and before we get started, there are a few housekeeping items. As a disclaimer, the views of today's speaker and organizations are their own and do not necessarily reflect those of the National Safety Council or Safety and Health Magazine. Any mention of a commercial enterprise, product, or publication does not mean the council of the magazine endorses those items. After today's presentation, we'll conduct a Q&A with our speaker. If you have a question, click the Q&A button at the bottom of the screen, type your question, and press the send button. We welcome your questions at any time during today's event. You don't have to wait for the Q&A to begin. We might not get to every question, but the good news is that unanswered questions will be forwarded to today's sponsors. Also, after this presentation, you'll be asked to complete a brief evaluation survey, and I'll tell you more about that a little bit later. Just to let you know, this webcast will be archived, so you can access it after today's live event. To view this webcast and all of our past webcasts, please visit safetyandhealthmagazine.com/events, or you may receive a link in a post-event email. With that, let's introduce our speaker. With us today is Zahir Juma, partner at eHazard. Zahir performs electrical workplace safety training, consulting, arc flash engineering studies, electrical incident investigations, and electrical safety audits. He's a member of the IEEE, ASTM, and IEC committees, and has contributed to the NFPA 70E standard. Zahir also currently serves as the editor/papers review chief for the IEEE Electrical Safety Committee. Again, we thank you all for tuning into this presentation. Zahir, whenever you're ready, go ahead and take it away.
Thank you so much. Good day, everybody. So I have to give you the background of today's topic. It was very interesting. We received a telephone call from a company out in New Zealand, and we were talking to them, and they asked us, hey, you folks are experts on electrical safety, specifically arc flash and electrocution, electric shock safety. And we've got a particular challenge where we've got high voltage folks that are working on low voltage, and we found a lot of gaps. So can you all talk to them about low voltage safety? And these were all high voltage qualified persons. So that got me thinking. It got me thinking that if somebody is a senior at a high school, for example, you would expect them to know basic mathematics, right? So if somebody is high voltage qualified, you would expect them to move through the ranks in terms of instrumentation and automation, then low voltage, and then high voltage. However, in industry, that is not necessarily what we find. Some folks are high voltage qualified and understand high voltage safety exclusively. So the mindset change that we need is not so much expecting a senior to understand basic elementary school mathematics, but rather think of it as somebody with a finance major that needs to understand science, or somebody that has a completely science-based background that is now extracted from their field and put into a financial, commercial environment. Once we get thinking about high voltage and low voltage in that aspect, it changes our approach to what those rules are. Now, let me tell you where this started off for me. We were doing an arc flash study, an arc flash engineering study for a low voltage utility. And folks, we work everywhere. We are out at utilities on the one day, and the next day we are out in a big factory. The next day we are out in a small little factory with just 2 or 3 employees. All right, so it's a very diversified field. And one day I was out at an instrumentation type of factory, and these people do a lot of semiconductor type of devices and stuff. And next door to them was a high voltage substation. So we needed to get the information out from the utility on what the utility transformer specifications were. Now, that data, unfortunately, was not available by the plant, and the utility was unable to provide that information. What they did say, however, is that they're sending one of their very qualified workers out who has a lot of experience in that area. And so I meet up with this high voltage qualified utility lineman, and it's a senior gentleman, very, very knowledgeable. We're spending time out at the substation. We go through, we get some of the details, and then he tells me, Zahir, once you're done, I'll meet you out at the pad-bound transformer, because the nameplate for this transformer is on the inside of the transformer. So I've got to open up the door and get that data. And so I asked him, so can we do this safely? And are there going to be any exposed parts? And he says, no. I'm very familiar with this type of pad mount transformer. I know where the label is. It's on the side of the door, so there's not going to be any energized parts. And so he walks off, and I continue taking the rest of the data that I need. And I'm starting to walk up to him. And as I'm walking up to him, he removes the lock of this pad mount transformer. He opens up the door. He doesn't have any additional PPE like a face shield or any gloves. He's wearing arc-rated clothing, but it's daily workwear without any face or hand protection. And then he opens up the door and he laughs at the distance and he says, oh my gosh, I was wrong. Luckily, that was only 480 volts. Now, I want to ask you a question at this point. All right. The high voltage side was 13,800 volts. The low voltage side was 480 volts. Was there a problem? And was this worth a laugh when he said it's only 480 volts? And this is a very, very knowledgeable person, someone that I learned a ton of, someone that I got a ton of information from and held him in high respect for that 5 minutes that we were together before he went out to the pad mount transformer. So this creates that gap or that question that we need to ask. If you are high voltage qualified, can you be let loose in a low voltage environment? And that is what I plan to answer in this presentation today. Now, folks, one thing I want to do before I jump into the order of the day today is I would like to hear from you all in terms of what topics would you like to discuss? What would you like to see us present in the future? As we come up towards the end of the year, we plan the new year, and I would love to hear from you. What are some of the topics that you would like to hear, or what are some of the areas of development maybe, or areas that you feel are not being addressed adequately in industry and utilities that we need to speak of? So I would be greatly, greatly appreciative if you could drop me some ideas or some needs that you have, and we'll try to address those. All right, so the order of today is, I just want to touch very basically on some of the OSHA rules. We're obviously going to speak about what is electric shock, what is arc flash, what is high voltage, what is low voltage. So we're going to cover that first before we jump into the OSHA standards. Then I've got I think it's about 4 slides or so where I talk about, well, what is the high voltage mentality and what are some of the things that are required for high voltage that when you place those same mannerisms or those same behaviors or those similar work practices in a low voltage environment, how do those create additional hazards? So I want to talk about those, but I also want to speak about arc flash considerations. And then I want to conclude with the case history, some risk assessment guidelines that are required when high voltage persons work in low voltage environments, and then we're going to conclude. So let's start off with the basics. Let's talk about voltage, current, resistance, shock, and arc flash. Now, the best way to describe electricity is obviously using water, right? Because everybody uses a garden hose. Everybody has a faucet in their house. So everybody understands these concepts. And When we talk about voltage, when we talk about current, when we talk about resistance, we are actually discussing the three building blocks of electricity. Now, what is the analogy with regards to a water system? So imagine you've got a pipe. Now, the water in that pipe obviously has a certain water pressure. That pressure is analogous to voltage, and I hope I pronounced that correctly, to voltage. So the water pressure is akin to electrical voltage, all right? So you know that for water to flow, there's got to be a difference in pressure. So if the water in this pipe is at atmospheric pressure, is at the same uniform level, so gravity acts on it equally, that there's no water head or differential in that height, you know that you're not going to have flow. Similarly, for voltage, you've got to have a difference in potential. All right, so you've got to have voltage 1 and voltage 2 in order to have current. Now, what is current? When you have water in a pipe, the flow of that water is akin to current, because current is the movement of charge, right? So you know that these copper wires, these aluminum wires, these brass conductors, all of them have electrons, all of them have a charge on them. And as this charge moves, when exposed to this potential difference, this voltage difference, that is when we get current. So you can understand this. Think about your garden hose. Think about how thick that garden hose is, how thick the pipe is. And then think about the water main, the street's water main. You know that the thickness of the pipe changes between your house and the municipal main or the utility main. All right. The reason for this is to be able to handle that pressure. So when we talk about high voltage and low voltage, we talk about insulation to be able to maintain that voltage safely. One of the cheapest, nastiest insulations that you can get globally is air. The air that you and I breathe is probably the most common insulator that you can get. All right. So resistance. What is resistance? Resistance is the gauge of like, let's say, the garden hose. So the greater the diameter of that garden hose, the more flow you're going to be able to get. Okay, the greater the gauge of the wire, the lower the resistance. So as the resistance decreases, the current will increase. As the resistance increases, the current will decrease. All right, so let's play around with these concepts a little bit now in explaining some of these electrical hazards. So when you get, let's say, an uncontrolled rupture of this garden hose, when the garden hose just shears and bursts and there's an uncontrolled release of water from the system, well, that is what an arc flash is. It is when the voltage stress is that great that it ionizes, it breaks down the air and creates plasma. That plasma produces heat. All right, now how is that different from electric shock? Well, think about electric shock as the normal flow of water. So when that water flows through that garden hose and it flows through it normally, okay, it's doing good work. It's watering the yard, it's watering all of your plants and stuff like that. Similarly, when electricity flows through your HVAC, through your machine, it is doing useful work. But sometimes it accidentally flows through the body. And the other analogy that I have on this for electric shock is, think about normal current being drinking water. When you drink water, it enters your tummy and it moves through your body and it's great, right? When that water enters the wrong pipe, when it goes up your nose or when it goes down your air pipe, we've got a problem. All right, so we want to keep that current flowing in the right area. When the current flows in the wrong area, or it takes the wrong path through our body, that is when we are experiencing electric shock. I'm not going to get into the details of touch potential, step potential, but it's important to understand that arc flash is thermal, okay, it's heat, whereas electric shock, the mechanism is more of a neurological, neuromuscular effect, all right, on our body. So voltage levels, what is high voltage, what is low voltage? Low voltage generally is considered voltages below 1,000 volts. Now, OSHA decided to take a little bit of a different angle to this, where OSHA uses a simple value of 600 volts. What OSHA states is, and it's not directly, they do not state this, that high voltage is this, low voltage is this. What they state is below 600 volts is considered low voltage, above 600 volts it has high voltage rules. Right now, I understand that each one of you, depending on which area of the country you come from, depending on which country you come from, there's differences on what you consider high voltage and low voltage. Generally, for my discussion today, I'll be keeping voltages below 1000 volts as low voltage and anything above 1000 volts as high voltage, right? So what is the complication? What is the issue here? Voltage is voltage, right? So why are we making a big hoo-ha about this? Well, as the voltage changes, our system needs to change because, folks, it's about that pressure. I cannot take municipal line pressure and pass that through a kiddie straw, for example, or one of these cheap paper straws that you get, right? Because if I pass it through that paper straw, it's going to blow open because that paper straw doesn't have enough strength to be able to control that pressure, right? So as we get more voltage, we need more insulation. Now, folks, I can have a thicker cross-linked polyethylene covering, a polyvinyl chloride, a PVC covering over my wire. And the more thicker this insulation becomes, or the more complex it becomes, the greater the voltage it can handle. But something magical happens. As voltage increases, it magically couples with other conductive systems, right? And you all know this. When you get a lightning strike a mile away from your house, it can blow out all of your electronics. And what happens is it's that invisible magical coupling that occurs that's called induction. Now at high voltage, as the voltage increases, induction, that electrical, invisible electrical coupling becomes more of a concern. All right. So what we want to do is when the voltage becomes that high that I physically cannot cover it anymore, what do? All right. If I cannot beat them, I got to join them, which means that instead of protecting myself and insulating myself against that voltage, I now got to jump up to that voltage. And that is why you have this bird on a wire type of analogy. You can have somebody sit on a line that's 1 million volts, and that person is then on 1 million volts. But folks, 1 million volts minus 1 million volts is 0 volts. If you have 0 volts, you cannot have current, and current is the killer from an electrocution point of view. Hopefully that makes sense to you all. What happens in low voltage? Well, power is power, right? The transformer is converting all of this power and it's sending it out to your factory. It's sending it out to your substation. So what happens as the voltage comes down? Folks, in the previous slide I showed you, like you have pressure and flow that creates the power in your water system. Similarly, the power in my electrical system is a function of voltage and current. So you start off with very high voltages and low current, right? That is what the utility is transmitting. And then you come down to lower voltage, which is coming into your house, which is coming into your substation, which is coming into your warehouse. You've got lower voltage, but higher current, right? Power, energy, neither created nor destroyed, but merely transferred from one object to another. So what happens as the current increases and the voltage goes down? Well, folks, as the current increases, you're getting more flow. More flow means more heat, right? But also with current, you get very high mechanical force considerations. So at higher voltages, where you're getting induction as a concern, at lower voltages, you're getting heating, you're getting mechanical forces being more of a consideration. Now, here's where the complication also arrives. OSHA has different standards for high voltage and low voltage. And folks, I know of several experts out in the field that tell me it takes a lifetime. And I can tell you because I'm a pretty old guy now. So I can tell you it also takes a lifetime to become an expert in each one of these. All right. And some of us are lucky enough to actually get to play in both of these. So let's talk about the high voltage and low voltage rules. Now, this is a little bit of a deviation from the core of today's presentation. I've just added in it in there because we have so many questions. A very, very boring section. I'm going to read through the slides. So if you need to snooze for 30 seconds or a minute, now's a good time to take that snooze. All right, so let's talk about low voltage commercial systems. These folks follow the OSHA rule, but they also follow a standard called the NFPA 70E. It's the standard for electrical safety in the workplace. And these rules are very different. So these folks are governed by loosely the lockout tagout requirements and the work practice requirements. Now, these are slightly different from 1910.147. All of you who are safety and health practitioners, you all may be very familiar with 1910.147. However, 1910.147 actually excludes electrical control of hazardous energy. So lockout, tagout, electrical, they actually point you to subpart S or subpart R. So the lockout, tagout requirements in subpart S basically say that for low voltage, okay, and I'm kind of contradicting myself here, and I'll tell you why by the next slide, is that for low voltage, what they state is you've got to have a written procedure. You have to explain how are you releasing stored electrical and non-electrical energy. Folks, all of you are familiar with this. I'm going to go through this quicker. 600 volt test equipment and higher shall be verified immediately after testing. Almost all of us perform an instrument test both before and after testing the system, right? So it covers induced voltages, but only from a testing standpoint. It does not tell you how to work on these voltages, all right? Or how to work safely around induced voltages. And it does not stipulate the use of any temporary protective grounds. These are grounds that we that we hang on high voltage systems, except for capacitors. So going on, if you look at Article 333, which talk about the work practices when you're working on or near, they say it is limited to qualified persons, and then they refer to 1910.2694, these work rules. And they tell you that if you are an unqualified person, remember folks, if you are high voltage qualified, you are unqualified to work on low voltage. If you are low voltage qualified, you are unqualified to work at higher voltage. So what they state is anybody who is not high voltage qualified needs to maintain at least 10 feet clearance for voltages up to 50,000 volts. And then they've got a little rule out there, which you all can figure out in your own time, all right? So qualified persons may not cross what they call the minimum approach distance. Now, folks, loosely, we refer to the MAD boundary, the MAD, the minimum approach distance. We refer to the MAD boundary as a qualified person's boundary. And if you broach this boundary, if you cross over this minimum approach distance, you are considered performing live work. Very important concept, okay? So when you perform this live work, there are two requirements. Number one, you need to be covered up to protect yourself, right? So you're putting on that insulation around you to make sure that the voltage cannot jump over into your body and cause current to flow through your body. You're insulating yourself. So if you've got 4,160 volts, you are covering yourself up from head to toe to make sure that the 4,160 volts sees so much resistance that it just says, oh, this is not worth my time, and it goes and causes current to flow somewhere else, all right? Or alternatively, if you cannot cover yourself up, you cover the energized equipment. So then you take all of these blankets that have an insulation rating that is appropriate for this voltage, and you cover up all this exposed energized systems. Now, here's the problem. Subpart S alone is inadequate for high voltage safety. Why? It is because it doesn't specifically tell me what to do around arc flash safety, and it has no specific, and let me be clear here, arc flash safety for higher voltages, and it also has no specific work rules for high voltage besides it pointing you to 1910.269. All right, I've added some of those distances in that table. I'm sure all of you are reading well ahead of me. So everybody says, don't make your slide look so busy. So I really apologize for this. It is probably only one of 2 or 3 slides that looks this busy. So let's break through this very quickly. All right, 1910.269 says that what is excluded, and they say electrical installations, electrical safety work practices, or electrical maintenance considerations covered by subpart S of this part. And folks, subpart S generally refers to commercial industrial installations. Not true, because as I mentioned in the previous slide, if you think that subpart S is for low voltage alone, then why have they put in high voltage considerations? Why did they tell you if you're unqualified, keep this distance away? So there are some considerations in the low voltage standard that speaks to the high voltage standard and vice versa. And I want to talk to you very quickly about this OSHA letter of interpretation. Folks, this is super duper critical. All right, and what it says is that an employee may be cited for a violation of the general duty clause under section XXX of the OSHA Act whenever any employee would be protected under one standard when the other normally applicable standard contains no provision, right? And let me tell you where this gap exists. Let's say you have an industrial setup and your utility brings out a power line, an overhead power line, stops there and says to you, company XYZ, here is your takeover point. Everything from this fuse belongs to you. The cable, everything, you own everything. And they bring in 12,470 volts. And you think, my goodness, how am I going to get this power to the other side of the plant? Oh, okay, let me call a contractor in. Let's put in some power lines in here and let's get this voltage sent over to the other side of the plant. So you install these wooden poles and you've got some overhead lines. Guess what? You are not a utility. You are not selling this power for the purposes of generating revenue, okay? You are not a utility. But unfortunately, the standard that applies to you is subpart S, but subpart S doesn't cover the specific safety rules. For example, how do you calculate your over voltages? How do you know what type of fusing you need to use? How do you know what sort of training is required? How do you know what type of insulation is required on your bucket truck, etc., etc.? Okay, so that is why OSHA states that if the rule that applies to you doesn't address your safety or your hazards, doesn't address your hazards adequately, then you need to refer to any other standard. Now, folks, this is not a one-way valve. It's not a one-way street, okay? It's bidirectional traffic, which means that low voltage persons in high voltage environments will need guidance as much as high voltage people in low voltage environments would need guidance. And I hope I said that the right way around. All right. So there needs to be a clear delineation between the two. High voltage specific training and the determination of high voltage qualified persons, very important. So the highlights of 269, you need one person that leads a job. This is the high voltage mentality. All right. So this is the rules that high voltage folks live by. Right? So you have one person that leads the job. Job briefings are compulsory. Even if it is one person, all jobs must still be planned. The control of hazardous energy, right? Your lockout tagout procedures must be written. Employee training, inspections required. And there's a section in here for transmission lines which says, and folks, let me just talk about this for a second. If you see a physical gap on two sides of a high voltage line, like physically the lines are broken, you still have to assume that these lines are energized until they are grounded. And when you ground, you create an equipotential zone. I'll talk about that in a second. All right, appropriate PPE and guidance for the energies now, or the voltages rather. Now, let's talk about low voltage and high voltage hazards. Here's the core of my presentation. Part 3 is the absolute core of my presentation today. And let's see if you pick up something that's useful to you. All right, now picture this. I am a high voltage qualified person. All right, not that I'm claiming to be, but imagine that I'm a high voltage qualified person and you have just sent me into the warehouse because there's a 208 volt panel board that's supplying my protection circuits that's not working. All right. So to be able to get into that area, and I'm just setting the background here, okay, just picture this or use whatever scenario applies to you all. All right. So now imagine that I'm this person now that enters this low voltage environment. What are the first considerations that I'm going to have? So let's see. grounding. What are the grounding rules? Okay, so under high voltage, it is mandatory to install grounds on high voltage lines. If there's no grounds, you assume that the system is energized, right? Grounding shall be used to create an equipotential zone. Now, folks, I don't want to get into an equipotential zone discussion because I need an entire presentation for that. But let's talk about this very clearly, sort of as clear as I can be. All right. Whatever happens here, if you look at these lines, all of these lines are connected to each other. They connected to the area at which this lineman is standing, and they connected to the neutral conductor, and the neutral conductor in turn is connected down to ground. What that means is whatever happens to the system, everything's going to move appropriately. I'm going to talk about this in the next, we'll move with the same potential. All right, means that if voltage 1 minus voltage 2 is 0, then you're not going to have any current through this worker's body. So the high voltage rules want you to apply grounding in such a way that you establish this equipotential zone, EPZ. The low voltage rules say that grounding is not required for lockout tagout and insulating is preferred, right? So high voltage person goes in there and says, well, I mean, what harm am I going to create if I just connect everything together and connect it down to ground? Because that is what we do at high voltage. Well, folks, remember what I said. As the voltage goes down, the current goes up. As the current goes up, the forces, electromechanical forces, increase to the square of the current, which means that if there's a low voltage fault, you're going to create multiple voltages circulating everywhere, different voltages. You're going to get grounds that are going to be blown out. If the grounds are not blown out, the grounds may cause enough force to cause whipping actions in the vicinity that a person is working in. All right. It's like almost like a motor effect. All right. So we cannot have that. And you may be thinking that what you're doing is great because, hey, what can go wrong? I'm adding another safety intervention, but you know what they say about the road to hell, right? So, and excuse my language. I know my kids completely and utterly freak out every time I use that word. So I should have said HE double leg. Okay, so so let's talk a little bit more about equipotential zones, right? So remember I told you previously V2 minus V1 is equal to 0, right? The idea is we want you all to float together, right? Like Pennywise famously saying, down here, we all float, they all float, Georgie. All right, so when you've got this line and you've got this high voltage line, we actually want the entire system to increase and decrease, right? So if you have 1,000,000 volts coming through that line, we want the worker to jump up to 1,000,000 volts with that line. Okay, folks, 1,000,000 minus 1,000,000 is still 0. That is how high voltage folks create safety. They use grounds and they ensure that the worker is grounded as well, right? Sometimes you'll have the worker stand on a metallic, a copper a based mat that is connected to the electrical system and connected to ground at the same time. Why? You want that worker to be conductive. We're supplying high voltage workers with conductive suits these days. All right. That means that any current that flows on the outside of that suit rather than the worker, and making sure that the voltages are all normalized. At low voltage, we don't want to ground for an equipotential zone, but what we want to do is we want to cover up. We want to cover up the equipment. If we cannot cover up the equipment, we want to use gloves. We want to use insulated shoes. We want to use electrical rated hard hats. We want to use rubber insulating gloves. I think I said rubber insulating gloves twice. Well, maybe because it's so important. All right. Now, let's talk about the other area. So grounding was one, right? I'm finished with grounding now. Now let's talk about safety checks. In high voltage, sometimes you have somebody listen for impending failure, right? But at low voltage, folks, you don't get so much corona. Corona is that arcing, is that that crackling high voltage sound. And I'm sorry, I did a terrible impersonation of the overhead lines. So, but at high voltages, you actually hear that sound. And when that sound is not audible, you have ultrasonic devices that can pick up those sounds. Well, folks, at low voltage is extremely quiet, extremely quiet. Even with ultrasonic sensors, sometimes they don't have enough resolution to be able to pick up impending failure. Generally at low voltage, you have a runaway, whereas high voltage, you get corona forming, you get pitting, you get expansion of the corona region, and then you go into a breakdown. At high voltage, it's you go from hero to zero immediately, near immediately. I mean, it's a magnitude different compared to high voltage. So even our safety checks, listening for high voltage does not work at low voltage, all right? Higher voltages, you outdoors, you have sun, you have reflection of the surface heat. Doing an infrared on it may not be as effective as doing an infrared thermal imagery scan for low voltage. So at low voltage, we rely more on infrared, whereas at high voltage, we rely more on ultrasonic. Now, folks, please don't throw me under the bus for this. I'm not saying that these are the only safety checks we have. There's many, many other safety checks. One of those safety checks is tools and testing equipment. So at low voltage, testing is considered touching the equipment. So when I take meter probes, as you can see on this bottom left-hand picture, when I hold that meter in my hand, when I hold the voltage probe, I am considered, or those pieces of equipment are physically considered an extension of my body, all right? That means when I measure a system, measure for voltage at low voltage, I am considered part of the system. However, at high voltage, their approach is different. When they use a live line tool, like you can see on the top right-hand side, at a higher voltage, a person using a live line tool, for example, you can see that they are not considered they do not consider testing as touching, right? Because they are trying to stay out of this minimum approach distance. And the minimum approach distance for high voltage and low voltage are completely different, all right? So at higher voltage, your live line tools are considered to insulate you from the system. So testing isn't considered touching, right? And here's another important thing. At low voltage, what do we want to test for? We want to test for 0 volts, am I right? We want to test for 0 volts. At high voltage, we hardly ever test for 0 volts. At high voltages, we want to test for the absence of nominal voltage. When we don't have that voltage, for example, if it's a 13.8 kV system or it's 115,000 volts, we're not testing for 0 volts. We're making sure that that 13.8 kV or 115 kV is not present. Why? The next thing we want to do is we want to apply grounds. We want to create an equipotential zone. And yes, folks, even at 13.8 kV, at 4,160 volts, you are expected to create an equipotential zone if you are getting into the system. All right. And I know that is a very contentious topic. Folks, I would love to have that discussion with you. If you feel offended by what I've said, please reach out to me and I'd love to talk to you. All right. So high voltage induction implies a clean zero, whereas high voltage implies that a clean zero is not possible because of induction, whereas at low voltage, you're always shooting for 0 volts. So let's talk about the protection. And now, folks, I use the word dielectric gloves here, but you do get cover-ups as well. So for systems below 1,000 volts, for example, you do actually get rolls of protective covering sheets that you can actually roll out. It's like blankets and you can cover up your low voltage system. You do get those at higher voltages as well. All right, but there are limitations. So if you look at low voltage gloves only go up to 36,000 volts. All right. Now, brace yourself, because what I'm about to say is maybe shocking to a lot of you, but at high voltage, we've got something called a bare hand rule. Okay. That means that the voltage is that high that you physically do not have a glove to work at that voltage. What OSHA allows you to do under what OSHA allows you is something called bare hand energized work. All right. Now, we've got to be very careful, folks, because this is a very, very, very specialized topic. I do not expect you all to take my word for anything I'm saying here and implement work practices on this kind of little snapshot that we're discussing today. But you may have somebody that does live line work. What they are doing, folks, is they are actually getting up to that 1,000,000 volts that I told you. All right. So if they are at 1,000,000 volts, they don't want anything that creates resistance between them, because as soon as you get resistance, you're going to get a voltage drop, which means that you're going to get voltage 1 and voltage 2 not being the same. So what they want to do is they want to be in this equalized potential. Okay. And so bare hand is never, ever allowed in low voltage. In fact, there are several rules which require hand protection at low voltage. So there's great room for error, especially when people think about 208 volts or 240 volts, because people may believe that, hey, I work on the system in my house all the time. I'm not using a glove. Why do I need a glove now when I'm in a factory? Okay. And at low voltage, you always need that glove. There's very few exceptions in low voltage where you do not need the glove. And now I think the final, I think this is the final that I have on the LV versus HV hazards is maintenance requirements. So at high voltage, gloves can only go up to 36 kV as per ASTM D120 and need to be maintained electrically tested on a 6-monthly cycle and obviously inspected before every use. Liveline tools dielectrically tested every 24 months, bucket trucks, hoses, insulating blankets, etc. All of those are tested 12 monthly, right? So inspections are obviously, whether you high voltage or low voltage, inspections are mandated before every single use. And high voltage equipment, we look at ultrasound, we look at thermographic testing like infrared temperature testing, as well as partial discharge. Partial discharge is to be able to pick up that corona and that arcing. Low voltage, on the other hand, voltmeters, multimeters, insulated tools, rubber insulating mats, EH-rated shoes, etc. Folks, after you buy those things, they don't need any inspection. I mean, any maintenance or testing on them, right? There's no rules for it. They tell you you can have a cursory glance over it, but there's no electrical stress testing as you get in high voltage. All right. So maintenance even has different requirements for high voltage and low voltage. All right. So now let's talk about arc flash considerations. Let's start off with low voltage calculations. Now, folks, for low voltage calculations, OSHA is very clear and says that IEEE 1584 is the recommended standard. Now, at the time of writing of OSHA back in 2014, they referred to 1584 and the 2002 standard was in force at that stage. Now we've got the 2018 standard and that is widely used. Now, the great thing about the standard is it allows us to go up to 15,000 volts. That will cover nearly every single commercial industry that's out there, because most of you all will buy your power at 13.8 or 12,470 or 13.2, or I've seen some crazy, weird, unique voltages as well, right? So you also have the option to use the NESC and 1910.269 Appendix E. However, most low voltage folks default to software. There's 3 very famous software packages that's used. That's Easy Power, SKM Power Tools, and ETAP. Any one of those 3 systems implement the IEEE 1584 standard for your arc flash calculations. Now for high voltage, all right, once you start getting above that 15 kV, the 1584 model, the IEEE equations start becoming overly conservative. And because of that, OSHA recommends that we use Arc Pro. It's a proprietary software that's based on some empirical work that was done at the Kinetrics laboratory out in Toronto. Now, the NESC Part 4 also has work rules, several tables that we use for high voltage calculations. So if you have transmission lines, if you have distribution systems that are more than 15 kV, even if you are below 15 kV but have overhead lines, it is best to default to ArcPro, the NESC, or the guidelines provided in Appendix E of 1910.269. Now, high voltage power lines have two saving graces for us. Number one, because of live line tools, because of bucket trucks, they allow us to work further away. That means being further away means there's a lesser chance of us coming into direct contact with the line and being electrocuted. But also, as you increase distance, your arc flash energy starts decreasing. The other factor that we've got, and this is a big one, when you're outside, you're in an open environment, arc directionality is very important. So you may have an arc flash and only part of the fireball engulfs you. Most of the core of the arc maybe moves in the opposite direction. Hey, but if you've got bad luck that like I do, trust me, that arc's going to chase you and land up on you. All right. So obviously we never take a chance with this. So utility workers at high voltage use the minimum arc rated and shock PPE. Why am I saying why am I making such a contentious statement? Because folks, if you look at it, for all of the arc flash studies that we have done on transmission lines in high voltage distribution yards, etc., because of the way that the protection is set up, because of the increased working distance, they will get out to an 8 calorie or a 12 calorie per centimeter square ensemble and would be adequately protected. You get out into high voltage environments, and some of these panel boards alone have like 12, 13 calories per square centimeter on them. Some of the switch boards have like 70, 80 calories per square centimeter. So this is very important. And here's the point of the arc flash and safety consideration. You all can read this while actually, let me go back to the slide. I don't want you all reading that just yet. All right. So here's the crux of it, folks. When we talk about high voltage, we are more interested in electrical shock safety. Okay. That is the greater hazard. Once you get down to low voltage, the arc flash energy becomes a greater consideration. Now, please don't go out trying to hang me out to dry because of the statement that I meant. Folks, more people are killed because of electrical shock than people are killed because of arc flash. Workers are electrocuted and obviously killed at 120 volts in commercial industrial settings. Electrical shock does kill people, all right? But at high voltage, a lot of our safety rules is trying to get us away from that electrical induction, electrical shock, electrocution, okay? And that's where a lot of everything is placed. And then you get the arc flash calculation. Obviously, these are two completely different hazards. But if you take that high voltage mentality and the way you work at high voltage and come into a low voltage environment, you're going to be protecting yourselves against the wrong things. Similarly, if you're a low voltage expert and you get into a high voltage arena, you are going to be protecting yourselves against the wrong thing. Okay. Now, folks, this is just continuing on the LV tables. NESC does have rules. Okay, another contentious slide here. All right, and what they say is that 8 calories per square centimeter should be adequate for all voltages below 250 volts. And they note variability between 251 to 600 volts. Okay, and you can read these 4 bullet points. Sometimes you get 40 calories, sometimes you could get more than 40, sometimes you get less than 40. So there's 2 challenges here. Challenge number 1, most utilities do not use arc flash labeling in transmission and distribution systems. What that means is that these workers are not comfortable with a label. They may not have received training to read and interpret a label. The second challenge we have is that there have been white papers published where we actually show that these tables have limitations, right? If you look at some of the NFPA 70E tables, you look at some of the NESC tables, when you come down to low voltage, because of the variances. Now the tables has notes. You're not going to be able to take the IEEE to court and sue them for this because they've got notes, they've got exclusions, they tell you to use engineering judgment, etc., etc. But if you are the poor person that accidentally took those tables without reading those footnotes, oh, by golly, you are going to be in so much trouble if something goes wrong. Right, so let's talk about this case history very quickly. I've run a little bit over time, but just as last summary, we'll go through very quickly. So what happened here, folks, it was late at night and they had a pad mount switch which brings the power in and then sends it to 3 or 4 different circuits. They had a problem with this pad mount. It had failed. Now, the supervisor who was there is been there forever and a day, very, very vested in the company. It's like, this is my equipment. This is my people that are being supplied with electricity. I have a personal responsibility to ensure that the system is safe. Okay, very vested, the true type of worker that you would love to employ. So what happened was some of the apprentices that came over that evening to fix up the circuit were inexperienced by his standards. So what happened was he was there. I mean, he worked a double shift already. So he went home, freshened up, came back early in the morning, and he said, I wonder whether these people did a good enough job. So he opens up the door and he opens up the low voltage side to go and inspect. And remember, this is a high voltage utility lineman, high voltage lineman, right? And he gets in and he gets into the LV side. And as he gets closer to inspect, his hand comes too close to the low voltage side and there's an arc flash, right? He was using his daily workwear and uniform. However, and I see this almost in every accident, didn't have a face shield, didn't have a balaclava, didn't have additional hand protection for the incident energy. So my question to you is, if this was a low voltage qualified person, would they have requested a label? Would they have had different work rules? Would they have understood the low voltage boundaries? And folks, this case history summarizes the problem. It summarizes the problem. We are now in this environment that we're finding ourselves where we have less and less skilled workers on our team. We are now asking people to take on more responsibility. You've got a high voltage lineman that's been pulled into a substation to go and troubleshoot a 208 volt circuit. 208 volt circuit, because that 208 volt is supplying the entire protection system. You've got a utility lineman worker working inside an administration building because there's something wrong with this transformer. You've got this person going into a warehouse because there's something wrong with this panel board. And we are the ones who are exposing our high voltage workers to low voltage. So folks, this presentation is going to be sent out to you. So I'm going to skip through the risk assessment guidelines. I know this is probably the highlight of the presentation, but you got to ask yourself, okay, I'm not going to skip it. I'll go through it very quickly. Is a worker low voltage qualified? Is the task a low voltage qualified? Yes, a low voltage task, yes or no? If there's any discrepancy, you've got to rethink who you are sending out to perform this work. Then, are shock hazards adequately addressed? Are arc flash hazards adequately addressed? Do not just think of these shock and arc flash as one. No, folks, they're two different electrical hazards. Okay, is the arc flash hazard analysis, your engineering study, is it up to date? Consider the absolute minimum guidelines. Obviously, you would need to do a lot more. So what are conclusions here? Not all high voltage qualified workers understand the inherent risk of shock and arc flash at low voltage, right? You've got this double knock system where your worker and your safety management system may be not working in concert with each other. High voltage qualified workers interact with low voltage. And I told you I'm seeing more and more of this, all right? Perform a detailed arc flash hazard analysis using 1584-2018, all right? Make sure that it is updated. Make sure that it covers all your systems below 15 kV. Provide labels. Folks, you won't believe this, all right? And I'm not having a dig here at utilities, but I've been to so many warehouses, so many administration buildings that belong to utilities that have not had an arc flash engineering hazard analysis or an engineering study performed. Now we are sending workers in this environment, they thinking, hey, it's only 480 volts, and laughing, all right? It isn't just that. It isn't about the shock. It's about the arc flash consideration as well, all right? So let's not rob off our people of the necessary tools that we need to provide them to be safe. All right, ensure that your maintenance is also in place. And folks, with that, I'm going to conclude and hand over to the moderator.
Well, thank you so much, Zahir, for this fantastic presentation. Before we start the Q&A, we want to remind everyone of the evaluation survey we're asking you to complete. The survey will open in a different screen after this webinar. Your input is important because it'll help us improve our future webcast. And as a reminder for our attendees, if you'd like to ask a question, feel free to click the Q&A button at the bottom of your screen. And if we don't get to your questions, a reminder, all unanswered questions will be forwarded along to our speaker. So our first question, can a safety professional, not an electrically qualified person, use a basic voltage present or not present testing tool near exposed wires from an uncovered junction box or electrically operated equipment to determine if it's lived, or should it be covered?
Oh, I think if I heard you correctly, that first part says not electrically qualified.
Yes.
So when you are using a testing tool near exposed wires, you are performing low voltage electrical work. And low voltage electrical work is reserved for either task qualified or low voltage qualified. What is the difference between the two? A task qualified person is somebody who only has certain work rules and can only do certain things. So for example, let's say I'm task qualified and you only train me that, Zahir, whenever you go to this panel and you are using this voltmeter, here's your gloves. Here's what you got to look on the gloves. Here's how you read that label. Here's what you are allowed to do. But more importantly, here's what you are not allowed to do. All right. And that's where my work would stop. However, a low voltage qualified person is somebody who then can then take the next step, open up that equipment and troubleshoot inside that equipment, even while the system is energized, obviously with the correct safety protocols being in place, right? We're not just being willy-nilly about this, just get in and find the fault. No, absolutely not. But I'm going to say there categorically, no. If a person is not low voltage task qualified or low voltage qualified, they cannot use a basic meter. And when you say a basic meter, I hope you are not talking about the pencil kind of non-contact, because those are not allowed by the NFPA 70E, which is the consensus standard. And oh my gosh, you would be in so much of trouble if you're using that for the purposes of lockout, tagout. All right, thanks. I hope that answers your question.
Our next question, are you aware of any electrical glove requirements to be used by HVAC techs?
Oh yeah, generally our minimum requirement, you won't believe this, we've actually just recently come out of an accident investigation at a hospital where an HVAC tech came into contact with low voltage, and this person had a pacemaker. So fortunately it didn't end very bad, but it was quite a disaster. So in this case, my recommendation would be rubber insulating gloves with overprotectors. You can use leather overprotectors. And these days, there's now other overprotectors that can be used, which offer better cut resistance, that can be used with rubber insulating gloves. Folks, at minimum, a class 00 electrical glove to be used.
Our next question, if testing for voltage on an outlet and the outlet covers on during testing, do you need to wear gloves?
So the rule for this is very simple. What OSHA states is no shock hazard below 50 volts. And then NFPA 70E says if you are working above 50 volts, and they talk about 50 to 150 volts, they say do not avoid contact. Okay, so what they're saying is you cannot contact this, and as long as you do not make direct contact with it, you do not need a glove. Now, as I mentioned during my presentation, testing is touching. So when you stick those probes inside that receptacle, right, those probes are an extension of your body. So testing is considered touching at low voltage, which means you have to be gloved up. Folks, it is a very unpopular sentiment. People hate me for saying this. Don't kill the messenger. Don't kill the messenger. I'm just here to make sure that you don't kill somebody.
Does the OSHA definition for energized, de-energized, and previous energized for high voltage apply to low voltage?
Ooh, so interestingly, OSHA, I'm I'm not 100% sure I understand this question. It's the definition for energized is, so at high voltage, anything that's energized means that it has not been grounded. That's at high voltage. At low voltage, you can have a system that's de-energized without it being grounded. So I'm going to say the definition of energized per HV will not apply to energized for LV.
I guess as we wrap up here, there's any other resources you would recommend for people to learn more about working with low voltage?
Oh, definitely. One of the biggest starting points for anybody is to take an electrical safety class. Electrical safety trainers are mushrooming across the country, and we should be scared about that. But I'm actually a little bit happy about that because it makes access to training a little bit easier to people. And thanks for the pandemic, we've got so many web-based classes these days. Please jump onto a basic electrical safety class that touches on NFPA 70E requirements. And any class is better than taking no class. And I know my employer is going to kill me for saying that, but do a quality check on who you use for your training classes as well. Very important.
Well, thank you so much. Unfortunately, we have run out of time for today. We'd like to thank Zahir Juma, the entire team from our sponsors, eHazard and Bulwark, and of course, all of you who joined us today. Take care and have a safe day.